Welcome to solverfy.
Okay, in this problem we have a hydrogen atom in two different states, the n equals 1 and n equals 4 state, and we need to find the de Broglie wavelength of the orbiting electron and compare it to the radius of the atom. So we're going to be using the Bohr model extensively in this problem. We need to know the Bohr expected velocity of this electron by the Bohr model, and we need to know the radius of this atom by the Bohr model. We also need the definition of a de Broglie wavelength for a particle with mass, which is simply the h over the momentum of that particle. For constants, we need the Bohr radius, a naught, which is given in meters, and h and c. So let's jump into it. So to start off, we can, using to find a de Broglie wavelength, we need to know the momentum of a particle. So we can start with the definition momentum, which is simply mv. We can plug in the Bohr model velocity for the electron, which will give us, when everything is all combined up, 1 over epsilon naught me squared over 2h, and then an n out here to -1. So this changes with energy level. So now that we have this, we can use the definition of a de Broglie wavelength, which is h over p, the momentum. Plug in this momentum and do some reorganizing. We have 2 epsilon naught h squared all over me squared. This is now multiplied by n. And we can, if we're clever, we can recognize that this expression right here is the definition of the Bohr radius. And we wouldn't need to necessarily know this to solve this problem, but it's just a little bit simpler. We don't have to do big computation at the end. So if we recognize this early, this will save some time. So the de Broglie wavelength for a particle as a function of the energy level n is 2 times the Bohr radius times n. Oh, and I missed one thing. It's not simply 2. There's actually a pi there. It's 2 pi a naught n. Okay. Awesome. So let's compare this to the Bohr radius, or rather the radius of the atom, which is simply a naught n squared. So at this point, we will see that for any energy level n, the lambda n over Rn will be 2 pi a naught n over a naught n squared. This is where the Bohr radius comes in handy, because you see it will cancel out, and you get 2 pi over n. So interestingly, as these energy levels increase, the spacing between adjacent energy levels in terms of the orbits is actually going down. So that's kind of interesting. So now let's get some numerical values. For lambda 1, we get 3.3 times 10 to the negative 10. This is when we actually plug in all of our constants. For lambda 4, we have 1.33 times 10 to the negative 9. And that's it. Main results. Thank you very much.